Yesterday I tried to explain it to my girlfriend, like, why is it interesting to study nanoelectronics? I thought the best way to explain it was by saying, well, you know how technology, if sufficiently advanced, looks like magic? Well, technically this is the closest way you can ever get to being a sorcerer. I like that. Nanoelectronics is about basically researching the gap between large-scale electronics all the way up to micro or nanoscale.
In nanoelectronics we study electronic structures which have nanoscale dimensions, so smaller than thousandths of a hair width.
We have our large-scale electronics, where we have big currents we can send through large wires, and we're getting huge magnetic fields. But if we do that at the micro and the nanoscale, that obviously somewhere should go wrong. I can't conduct that amount of current, so something should happen. What happens there? Is there something new? Is there something interesting? Is there a fundamental effect we're missing? And is there a fundamental effect we can actually use to improve upon our current technologies?
So nanoelectronics has an interesting position, I would say, in the range of specializations, because it's really at the intersection to applied physics. It has electronics in the name, so it's definitely an application of electrical engineering, but typically we focus more, or at least I do, more on the material science and physics kind of realm. So for me in particular, I'm in the clean room a lot. I do a lot of fabrication. So I've been actually doing a lot more chemistry and material science and things like that than electrical engineering.
So for the other specialization, you often incorporate entire circuits on maybe chips or devices. In our case, we're mainly interested in looking and seeing what's actually happening at the nanoscale, what's happening at these smaller sizes. We are not, we are mainly interested in finding which effects are there compared to building entire chips and devices.
But that's also up to you. So you can also ask for a project which goes more towards typical electrical engineering things in the lab and work with the electronic equipment.
You do a combination of work that is hands-on and sometimes a bit of also some theoretical background work. But the hands-on work is most important because we do experimental work. We make nanoscale chips to do electronic experiments. And in those electronic experiments we want to find out what's going on physically. So we want to understand the physics behind the electronics in our chips. For example, we try to use silicon to make quantum dots in them. And quantum dots means that we make small structures in which we can lock up individual electrons. And we try to see, so we've got a small lab with one electron on it, and we try to study the physics of a single electron.
One of the perfect examples is research led by Floris Zwanenburg. He is right now studying with his group the effect of one single bismuth atom and how that affects the surrounding around it. Can you, for example, build a quantum bit out of it? How can you use that? How would you actually read out what's happening there? Because, of course, a single electron, a single atom, can that be responsible for a difference in current? Well, yes, it turns out that it actually can, and that's so very interesting about it. How do we measure that? Of course, we need bright minds to get into that topic, research it. How do I read out? What can I make better? How can I improve that? And how would I find a future application for this?
And the two fields we study in our group are quantum electronics and neuromorphic electronics. In quantum electronics we study quantum physics in the electronic structures, and in neuromorphic electronics we study what we call brain-inspired electronics. And that's a completely new field where we try to be inspired indeed by nature, by the brain. The brain, which uses only 20 watts, but is maybe the most complex computer that we have in the world. And even though it uses only 20 watts, it can process things that a computer cannot process as efficient as a brain, like fast pattern recognition or speech recognition. So we try to be inspired by the brain, which is basically a complete computer in your head, which are all your neurons through each other, and we try to make something that looks like the brain.
Yeah.
And we're one of the leaders in the field in neuromorphic electronics in the world. Yeah.
Oh, okay, so no one else in the world is as far with this as you guys?
There's many people who try to study this, and we're at the front of the field. For example, colleague Wilfred van der Wield is coordinator of a European project called High Brain, which is again brain-inspired electronics specifically to to one topic.
The devices are getting smaller and smaller, the quantum effects are becoming larger and larger, and we have this intricate play of these different effects all at the same time. I'm studying nanoelectronics out of the interest I have in, for example, why does my phone work? Why do devices work? If you want to do the specialization, you have 4 compulsory courses. So first of all, you start with material science. Material science is where you be taught how different materials behave with different scales.
Depending on the material system, on the crystal phase, the crystal structure, how the atoms are bonded, things like that, you can have a complete variation of material properties.
Material science is meant specifically for electrical engineering students because they lack the background in material science that you need for the topics in our group. Because what we do is that we design our own experiments. And in these experiments we have a combination of electronic structures but also the materials, how they relate to each other. And that helps us to design the experiment for the physics we want to study.
Next up, nanoelectronics. This is what I'm particularly excited about.
Nanoelectronics is also basically set in 3 different parts. So there's basically like an introductory part into nanoelectronics. Then we have the 2 other parts which go deeper into the one part quantum electronics and the other neuromorphic electronics. So really like to represent what we're actually doing in the research group.
For example, in my case, I teach the quantum electronics part where we study quantized conductance of 1D structures, we study quantum dots, and we study the Aharonov-Bohm experiments. Those are probably terms that you've never heard about. And in general, it's about trying to understand the underlying physics of electronic structures. But now this is specifically about the quantum physics we can see in them. And quantum physics is a completely different realm where things are counterintuitive, where one object can be in 2 spots at the same time. For example, we study single electrons going through these nanostructures. We confine them in a little box, a quantum box, and we can see individual electrons tunneling through those boxes. Quantum dots, we call them. And to me, that's still the most exciting thing we do in our research. That's what students do in their bachelor thesis and master thesis. They study single electrons and observe them in the lab. That's one of the things we teach in the course, what is needed to observe individual electrons.
And what we also actually do in the course is we have to come up with our own project, how to plan it and how to realize it, and what kind of experiments we will do. So it's really good practice if you want to go further into research, actually.
So the kind of work you would do as a student is that you could be doing nanoscale fabrication. So you make your own chips in the clean room with the nanoscale structures. Then you test them in the lab. So you use the chip and you glue it on a printed circuit board. You connect the wires physically to actually do the experiments. Then you do the measurements. You measure the currents through your sample and try to find out what's going on. And most experiments we do at extremely low temperatures. And mostly for neuromorphic electronics, the low temperatures are 77 Kelvin, so minus 200 Celsius. But for the quantum electronic experiments, we go to much lower temperatures, to 4 Kelvin and even to 20 millikelvin, so very close to the absolute zero. And we need those temperatures to get the specific physics out that we want to study.
Okay, so very cool.
Extremely cool, we like to say.
Extremely cool, yeah.
You also have, of course, inside the specialization you have to do ethics. Ethics is a very broad topic and I can collapse it down for you. Don't commit academic fraud. To do this specialization, you have the 4 compulsory courses, however, there are 6 in total you'll have to do. The 2 remaining compulsory courses you can choose yourself. You can select them from this list. This list features different fields which you might be very interested in. For example, machine learning, extra quantum mechanics, but also semiconductor devices and integrated circuits.
I also liked integrated circuit technology because that kind of takes the technology to the next step, and you kind of learn how the fabrication and how the technology applies to the functionality of the device.
As well as a course that's called Fabrication of Micro and Nanoscale Devices.
So you really learn everything, I would say, there is to pretty much learn about fabricating your micro and nano device. So there's different deposition techniques, etching techniques, what kind of substrates you can work with. There's so much you learn in that course. And I think my favorite part is that you really apply that knowledge as well. So we actually get some kind of structure and we basically have to make our own process flow on how you could get to that structure. So you really have to come up with that yourself. And it's really fun for me, especially because now in my thesis I'm doing a lot of fabrication in the clean room. And then basically the rest of our courses, which is approximately half, is just free elective. So you can specialize even more if you want, or you can go into different fields that you might find interesting. So you can really customize your masters.
On the website you can find different courses that are best suited for this specialization direction. Also, you can choose other courses that were in the compulsory course list, but you can venture outward into different fields. For example, you can venture out into superconductivity. What is it? What does it describe? What happens there? You can study small signals in detection. How do I get a small signal from, for example, a cryostat or a quantum effect all the way back up to actually measure it? How does that work? You can choose these different courses freely and hopefully to your own interest.
And I think that's what this entire master, but also studying in general, is about. So use those compulsory courses together with the elective courses, because there's a whole other set, to get a program together that helps you get where you want to be, or find out where you want to be. Yeah.
The freedom is really what attracted me to the master in the first place, is the fact that basically half my courses were like elective space. Like, let's say I didn't have that freedom, I wouldn't be able to take some courses, or I would have to take an excess of courses. So I'm really grateful for that.
In the second year, you'll both be doing an internship and your final master's assignment. So the internship, which is about 20 ECs, you can do at a company, maybe you want to do it abroad, you can choose wherever you want to do it.
It's actually also up to you if you want to do your internship in a more research institute, or if you want to go to a company. As long as it's not at the University of Twente, you can go wherever you want.
We have contacts with IMEC in Leuven, where people have gone on an internship. And the person IMEC helped to design and measure electronic structures in a CMOS environment. So what I told you that we make silicon nanostructures, and we make them in our clean room. And basically, IMEC has a CMOS clean room, which is similar to the way real computer chips are made. That means that if one of those structures on their CMOS chips works, then it's easy for them to make them reproducible. And the student helped to design and simulate those structures, and also to test them in their electronics lab. It's a bit similar to what we do in our labs, but their specialty is fabrication and reproducible fabrication, and our expertise is more the quantum electronics experiments and understanding the physics. Well, Jonas Kareem has gone on an internship in Australia. Then he spent 4 or 5 months at the University of New South Wales in Sydney and did research in the group of a colleague of mine on silicon quantum dots.
So what I did is I actually asked my professor, because he has a lot of connections in Sydney at UNSW, if I could go there, and I got the okay. And I actually did my internship there at the university in Sydney, so it was a very long travel to get there. But after I did that, I was basically there at the research group, in the labs there, seeing how advanced they are there as well was also really interesting, and also comparing it to our labs. So I had a lot of fun on my project. I actually made this kind of probe. So basically what this probe does is, I've been talking about these measurements that we do. Typically we do them at very low temperatures. So I made this probe, which you basically attach your device onto, and then you put that into a tank of, like, let's say, liquid helium. And I designed and built this probe with all of its connections so that you can actually make those measurements at really low temperature. So I've heard they're like actively using my probe that I built. So that's also a really nice feeling that something you've done is actually being actively used. And yeah, it was just a very fun experience. I think I could definitely recommend it to others who choose NanoElectronics to go to Sydney.
For the master thesis, you first talk with myself or my co-chair, Wilfred van der Wiel. And then we talk about the different topics there are. And then we align you with one of the PhD students who has a project available. Then you need to look for the click, both in terms of the topic, but also the person. And then you choose whichever project is most suitable for yourself.
So likely you first search what you're interested in. Do you have a topic that comes to mind, for example, neuromorphic computing or quantum effects?
So as a student, you would choose between quantum electronics and neuromorphic electronics. And then within quantum electronics, you can make these kind of charge sensors or make nanowire transistors to try to understand their electronic properties. But in the neuromorphic team, you can also do different kinds of topics. You can be involved in the practical device fabrication and measurements on those structures to try to get the logic out of the strange brain-like structures. Or you can be more involved in the simulations if you feel more comfortable doing, let's say, the work behind your computer. For example, in neuromorphic electronics, we basically make a so-called dopant network. And that means that we implant specific dopant atoms, for example, boron atoms or arsenic atoms. We implant them in our structures and we use them to get that funny brain network that doesn't have a design. And a student has, for example, helped us to find out how deep we should implant the dopants, how can we activate them in the lattice, but also how do they then behave electronically. Are they indeed giving us the logic, and can we use them for this machine learning that we want to use?
I really enjoyed my courses, as I mentioned. I liked the integrated circuit technology course, fabrication of micro and nano devices. So it was a very nice and natural step to focusing on that in my thesis. I'm actually working on a new material, which is hexagonal silicon germanium. So normally you have silicon, you have germanium in a very traditional form. They're used all over the semiconductor industry, especially silicon. But this form of silicon germanium is basically has a different crystal phase. And because it has a different crystal phase, it has different properties. And what's most interesting, it has different electronic and optical properties. So for example, what I do is I look at these nanowires, and I want to make nanowire devices out of them, so I need to contact them.
We have a so-called micro manipulator, and that's a machine, basically a very pointy needle that we can control with an XYZ control to pick up individual nanowires. And those are so small that, of course, you cannot pick them up with a pair of tweezers, but you could consider this a micro tweezer. It doesn't have two arms, it just has a single point, and it picks up individual nanowires, basically using attractive van der Waals forces. Then you pick up the nanowire from the growth substrate, and we go to a clean substrate and you deposit it there.
It's a bit finicky, and you can also crash your tip into the substrate, so you don't want that to happen. But it's quite fun, especially the first times you kind of do it. It's nice. And basically I can then push an electrical current through them and measure the electrical properties, which is very useful for characterization. And later what we want to do with that is basically we want to put a gate on the nanowire. And so that's, if you're familiar with field effect transistors, you have a gate, and then basically you can control the amount of carriers in your channel. So I'm doing basically the exact same thing, but my channel is a nanowire. And in that way, if I can locally kind of tune the carrier concentration in the nanowire, I can also define an island of charge on the nanowire. And that's basically a quantum dot. And that's also the building block for making a qubit, which is the building block for making a quantum computer.
It feels like building, but like letting the building happen.
Yes, so the nice thing is that you can really be the architect of your own experiment. So first you need to understand, you need to find out what you would like to study. Then you need to think, how can we study this? And then you make the design with a combination of the materials, the electrodes, but also then the specific electronics that you need to observe what you hope to observe.
Yeah. And what if you don't observe it?
Well, so I often get this question, my experiment didn't work, what should I do? But the art is to also to get useful information from what we would call a failed experiment. I've written a complete journal article about a failed experiment because we did understand many other things, and that could help further the knowledge of science. So the research we do is very much explorative. We are not so much application-oriented, we do very fundamental science. And the applications are more in the longer term, like in 10 or 20 years from now, and not 3 years from now in industry. So I think we as a group are at the most fundamental side of electrical engineering. We also collaborate a lot with people from physics groups here at the university. So I sometimes call ourselves physicists in electrical engineering clothes. And most of the scientific staff members, but also PhD students, are indeed from a physics background. And we have a combination: physics, electrical engineering, nanotechnology. It's a nice mixture of all these disciplines.
Well, of course, during your master assignment, you've learned a lot about the academic perspective. And for some people, that is worth sticking around for. Actually, a lot of people stick around for their PhD to continue becoming an actual doctor inside the field. However, we're also preparing you for more broad scope. We're also preparing you for industry. What are they expecting? What would they like you to have already learned? That's all included inside this master.
So in general, we deliver, I would say, good engineers with these analytical skills. And one of my former students has now started to work, he already works for a few years, at Demcon. And he basically designs advanced electronics and megatronics. So that's a combination of the electronics and programming.
Well, of course, there are a lot of companies that are very much willing to have you. In terms of, for example, a big blue company in the south, ASML, or Thales, which is more close by, Q-Micron, also very close by, Lyonics, if you're in terms of fabrication.
Another example is a former student who started to work at a startup company in Delft. That's Q-Blocks. It's a quantum startup company, and they deliver specific measurement electronics for quantum research groups. So again, he uses his expertise that he picked up in our group to now help research groups with new electronics and help the startup to sell this and specifically tailor this for the research groups.
So yeah, indeed, I did my master's in applied physics, and now I'm a PhD in electrical engineering. When I firstly started, I was fully convinced I was doing applied physics. I was looking at all the stuff I learned during my master's over there. And as soon as I stepped into the lab on my first day, they explained to me, well, you need to connect this device to that device, and you need to now reroute this, and you need an amplifier between there. And I realized I had so little clue of what I was doing. I knew what physical effects I was hoping to see. I knew exactly what I was reading about. I know exactly what type of radiation I was hoping to measure one day. And then they come up to me and say, this is an electronics rack. I wish you the best of luck connecting that. And they do that to all their applied physics students, because then you realize you need electrical engineering in the field you're doing now. So then you start becoming more and more interested in the electronics behind it. What am I doing? How does an amplifier work? Because I've seen amplifiers, of course, during my studies. However, this one should be more and more noiseless. How do I reduce the noise? How do I do this? How do I specify the bandwidth I'm going to be measuring in? How do I connect all of that to my point of physics? And that's what I find so incredibly interesting, and that's why I'm becoming more and more interested in the electrical engineering aspect of it all.
Wow, that's really, you really have to bend your mind, like break from what you used to think about when you wanna.
Exactly. So that's the sort of tension you feel between, on the one side, maybe being a bit overwhelmed, and at the same time excited because it's so counterintuitive. And if that also excites you, then feel free to come to our group and then share the same passion, but also maybe the fear of maybe even being insecure about maybe not entirely understanding yet. But we try to express that and also conquer that, and that's extremely cool when you get over this threshold and just go for it and work with the fact that not everything has to be intuitive.
If you're interested in semiconductor device physics, if you're interested in integrated circuit design, if you're interested in quantum mechanical effects and studying the true behavior, what happens at those smaller scales, are you interested in all of that? And I think this nano specialization is the specialization for you.